Now we're ready to analyze some stressed objects, but first let's recapitulate what we've done thus far. We defined normal and shear stress, and with Newton's second law, developed a differential equation model for stress equilibrium. We defined normal and shear strains in terms of derivatives of the displacement functions. We used Hooke's law to substitute strain for stress in the stress equilibrium model, and replace strain with derivatives of the displacement functions to get an equilibrium model in terms of the displacement functions. Then we made the FDM substitutions for derivatives of the displacement functions to get linear equations for each interior grid point with the displacements as the unknowns. Now we're ready to apply these formulas. Ready, set, go. We're ready to analyze stress and strain in an elastic object. We'll start with a 2 by 2 meter square plate compressed downward. The parameters of the material making up the plate are Young's modulus is 3 and Poisson's ratio is 0.3. We will apply a downward traction of 1 Newton per meter all along the top surface of the plate. We'll use a 10 by 10 grid. The diagram shows the unstressed plate. Note that MATLAB doesn't square up the axes in a graph unless you tell it to, and I didn't, so the square plate doesn't appear quite square. We need to pay close attention to the boundary conditions. Along the top, there is a vertical traction of -1 Newton per meter, which produces a stress of -1 Newton per meter along the top boundary of the square. The vertical strain corresponding to that stress is, from Hooke's law, equal to 1 over E times the stress. So the vertical strain along the top is -1 over E, and since vertical strain is the derivative of the vertical displacement function with respect to y, we have the partial derivative of v with respect to y equals -1 over E, and this corresponds to a Neumann boundary condition of vi, 10 minus vi, 9 equals dy times -1 over E along the top boundary. There is no horizontal traction along the top, so we'll use a passive Neumann boundary condition specifying u of I, 10 equals u of I, 9 along the top boundary. There is 0 vertical displacement along the bottom boundary. That corresponds to a Dirichlet boundary condition on v of I, 1 equals 0 along the bottom. There is no horizontal traction along the boundary, and we're going to let it slide freely along the bottom, so we inherit the horizontal displacement from the row above it using a passive Neumann boundary condition of u of I, 1 equals u of I, 2 along the bottom. Boundary conditions for the sides. There is no vertical traction along the sides, so a passive Neumann boundary condition is specified for both sides as shown. There is no horizontal traction along the sides. However, the vertical stress transmitted from above causes a horizontal strain as per Hooke's law equal to minus rho times the vertical strain. So we use a Neumann boundary condition to model this strain. So on the left side we have u of 1 comma j minus u of 2 comma j divided by dx equals rho times v of 1 comma j plus 1 minus v of 1 comma j minus 1 divided by 2 times dy. And with x equal dy, this simplifies to u of 1 comma j minus u of 2 comma j equals rho times v of 1 comma j plus 1 minus v of 1 comma j minus 1 divided by 2. And a similar boundary condition is specified for the right side. This is a steady state problem, and up to now we have solved steady state problems by writing a set of n linear equations and n unknowns, one for each grid point, and then using matrix inversion to solve the problem. But we've only done that for small problems, and in this problem n equals 100 and the A matrix of coefficients will be 100 by 100, so we'd have to initialize an array of 10,000 elements and then hope that MATLAB could invert it. So we don't want to do that. And there is another way that will be much easier for us. It is known as the Gauss-Seidel method of solving simultaneous linear equations, and it looks a lot like time stepping. Here's how it works. At the top of the slide, we have the linear equations that we have derived for each grid point in the previous video. At the bottom of the slide, we have solved the equations for the displacements. That is, we have rewritten the formula so that ui, j and vi, j appear on the left sides. We can do the same thing for the equations for the boundary conditions. Now these equations are computational equations we can use to compute the solution directly in an iterative procedure. This slide shows the computational equations on the previous slide translated into MATLAB code. It's a literal character-by-character translation. The computational equations are included in a loop that computes the steady-state solution. It looks a lot like time stepping, but unlike the time stepping loops, we are not advancing time, and we are not updating uij using an estimate of the derivative of uij. Also, we do not save the old values and use them on the right side of the computational equation. We use the new values as they are computed. How many iterations? It is necessary to iterate the calculations until the solution stabilizes. Since the iterations are very fast, you can choose a big number and not worry about it. Up to now, we have scrupulously avoided non-essential programming. So each program has consisted of the loop to compute the solution, MATLAB plotting commands, and the bare minimum of other statements necessary to support those functions. Now, however, we must do a little programming. We want to display the stressed object, and I don't know of a MATLAB graphing command to do it, so we will program our own. UM and VM are arrays of the coordinates of the stressed object. The for loop computes their values. So, the x-coordinate of the ijth grid point in the stressed object is the original x-coordinate of the grid point, which is given by I minus 1 times dx, plus the calculated x displacement of the grid point, which is ui, j. Similarly, the y-coordinate of the ijth grid point in the stressed object is the original y-coordinate plus the calculated y displacement. Now, with these arrays, we can draw the lines making up the graph of the stressed object. The command plot j, vm, j plots the horizontal line connecting the jth row of the displaced grid points. The command plot umi, vmi, plots the vertical line connecting the ith column of displaced grid points. Here's what the result looks like. Notice that the original 2 by 2 square has been compressed downward, and it has also expanded horizontally. The assignment is to reproduce the results in the vid and then to run the program with 2 other sets of boundary conditions. In the second option, the bottom plate is fixed both vertically and horizontally, and in the third option, the bottom plate is fixed and the top plate is also fixed horizontally. The results for the second and third options are shown after the program outline.